Welcome everyone. Good to see quite a lot of people in this room. The next talk is about the digital approaches to improve steel manufacture in the future, and that's basically hosted by me, Michael Auinger, and my colleague Richard Thackray from Sheffield. The focus of today's talk is because we picked a rather large topic, we'd like to go a little bit into the background and the justification before we actually tell you what we are doing as a team in Sustain in Task 5, which is called, has the very interesting title, Intelligent Steelmaking. And then we conclude with a little bit of progress that has been made so far and a summary. So when one talks about digital approaches, well, without mentioning too much about the first 2 points, because you just heard actually 2 full-grown presentations on that, on data-driven or economics-driven approaches in order to improve a certain process. Richard and I would like to focus more on the engineering-driven side, which is actually using physical modeling and process engineering simulations and make those quicker and more efficient in order to predict the process as it happens. And that includes things like mass and energy flow. So here is an example. It actually mimics the blast furnace process. You divide a furnace into individual zones. That was part of an MSc project 2-3 years ago happening at Warwick. Within this zone, you assume thermodynamic reactions. So you can consider this as a bucket where you put all your ingredients in, and then you shake it and let your reactions happen, either in local equilibrium or kinetically controlled, as you see in the graphs on the very right-hand side. So what do we mean with process engineering simulations? As I already mentioned, it's more or less actually been seen as a framework of general building blocks. So you have individual blocks, meaning models working together. So there is the issue of data transfer. And in the end, you're analyzing that network. Initially, these solutions might be simple, meaning very quick and low fidelity models, and they will improve with time, of course. We have to improve. But this way, if you are focusing on this macro level approach, first, you will be able to quickly identify the critical process step. And I mean this in a quantified reason rather than in human intuition-based reason on what the criticality, the most critical process might be. And that puts a clear focus on further development. And ideally, these processes need to be fast, because we don't want to have actually a 3-hour simulation in order to predict something that's happening at the moment in an industrial plant. And this is part of what we are doing in Task 5. And I have to give credit to my RA, Arash, who came up with the very catchy title, The Digital Refinery, where we're actually trying to use these kind of fast process models and actually linking them together to go all the way from the blast furnace through the ladle to the caster. For those who are not too familiar about what I mean with physical modeling, I mean actually physics-based modeling. So for the experimentalists amongst you, I'm a theoretician, my samples are all digital. So with physical modeling, I mean physics-based modeling. These are very much simulations that help you to understand effects. And I did mention that the human intuition can be misleading. And a very classical example that I experienced myself is actually this publication that I published during my time at Max Planck in Düsseldorf about high temperature oxidation. I'm not quite sure if you can see the difference in these gray shaded areas between the 2 images on the right-hand side. There are 2 alloys that are oxidized, and you see in the left one there is a much deeper oxidation happening in an iron manganese silicon than happens actually in aluminium chromium. What the general approach of literature was actually saying that, oh, grain boundary oxidation must be enhanced in that systems. If you compare this actually to simulations, you will see that the grain boundary oxidation follows exact predictions as one would happen, but instead it's the internal oxidations in the grains, which is like this gray shaded area, the denser gray shaded area, that's actually hampered. So in other words, people were barking the wrong tree for a couple of years by following human intuition and looking at the image and getting the impression that grain boundary oxidation must be enhanced, whereas it's actually the internal oxidation that's slowed down. Now, this is not the solution of the process, but it's a very important piece of the puzzle in order to find a solution. What physical models can also do is you can very easily vary process parameters. And I mean this in a much broader context than you probably want in an industrial process. So you can use this to optimize the performance of individual processes, but you can also look at to test sensitivity of individual parameters. What happens if the temperature increases by 5 degrees? There might be fluctuations. What happens actually to the quality of the product? Or, as already mentioned, to go even further outside the usual range of operations, where you can test critical conditions that you never want to have in an industrial line, such as failure or sudden production stops. So you can use these kind of models as a digital playground for a what-if scenario and develop structures in order to recover very quickly from a situation that you usually don't want to test in real life. So how is this done? One of the challenges, though, is if you start off with individual models, well, we heard a little bit about neural networks that was in the area of machine learning, artificial intelligence. These models are usually very fast. You can process very large quantities of data through. On the other end, there is the finite element models that most people know. That's the numerical simulations. There are a lot of commercial programs out there where you model multiple physics-based phenomena. They are quite accurate, but take an awful long time to compute. So not really practicable. What we are trying in Sustain is actually that we're going a middle way in having a reactive zone model, and I'm coming back to that a bit later in this talk, where we try to marry together the benefits of the two models, being very accurate from the finite element side, but still being quite fast in terms of producing large quantities of data. And this is just another example of where such models can be used. I need to give credit to Marx, who is a PhD student of mine, who already is working in industry whilst writing up his thesis. What you see is a set of simulations of a complex CFD burner flame simulation. In fact, I don't want to go into the details because I could talk for hours on this topic in itself. But what you do is, if you run a CFD simulation, it takes half an hour. If you vary a parameter, you need to rerun the simulation. Now, you probably get the idea. If you vary a lot of parameters, or you have a lot of points to screen through in your uncertainty matrix, in your variable processes, you don't have the time necessarily to run a million of simulations, because it's like 500,000 hours that you need on a standard computer. So what Marx is working during his PhD is actually in using enhanced models, in this case, a polynomial chaos expansion, in order to actually reduce the number of iterations in order to reach convergence much quicker than it is with conventional techniques for selecting the randomness of the input parameters. And this is very interesting and important. This is work that's about to be published. Formally, the article is already accepted. The paper is not yet out. But there is another work we are trying to apply this also to an industrial line. Without going into too many details, it's about slab reheating, which also links to works that Cameron Pladel-Pierce is doing on the emissivity of an oxide scale. So that's the physics-based models that we are also using in our simulations. And with this, I hand over to my colleague, Richard.
Thanks, Michael. Good morning, everyone. A little bit of a change of focus and a change of tack now. It was really nice to hear Ian mention in his introduction at the start of this session, the idea of data-driven innovation. I think Michael's given an example of one use of data. And what I'd like to do for the next 5 minutes or so is to give you another aspect of that use and how we can use data in different ways. And I think it's that ability to collect and interpret process data and combine that with existing material data that's led to a huge increase in the number of assessment techniques over the past 30 years or so, and particularly over the past 5 or 10 years. Different assessment, different visualization approaches, life cycle assessment, life cycle inventory, material flow analysis, etc. And it was really pleasing to hear yesterday in some of the talks, in fact, many of the talks, the need for modeling and assessment of this kind in order to inform future pathways. So next slide, please, Michael. So I think we can go from a traditional LCA approach, a fairly simplistic approach, where we have on the left-hand side the calculation of various greenhouse gas emissions, both direct and indirect from upstream raw materials. And you can see that this has been done for both the BOS process, the BOF process, and the electric arc furnace process. And again, it was really nice to hear Jeff Brooks yesterday in his keynote, if you like, calling for a more granular and a more sophisticated LCA comparison of BOF and electric arc furnace steel. That was nice to hear, and I agree with Jeff. And we can look at that in a different way on the right-hand side, where in this case we've got the contribution of the different steps in the steelmaking process to various environmental impact categories. So ranging from the left-hand side, climate change, and you can see the effect of the BOS process and the blast furnace and sintering and the coke ovens, as you'd expect, dominated by the iron making side of things, all the way through to the right-hand side, looking at water resource depletion. And how the different steps affect each of those impact categories slightly differently. Next slide, please, Michael. We can also extend this in any number of ways, and this was some work we did some time ago that looked at calculating the additional CO2 impact of alloying additions for a number of advanced high-strength steels. And so we could sort of quantify the impact of substitution. If we wanted to substitute a particular element or a particular ferroalloy in this advanced high-strength steel, we could calculate the environmental impact of what that change and what that substitution would be. This helps us inform decisions regarding new grades and maybe new compositions that can be made by a particular steelmaking route. Next slide, please. Instead of using a traditional LCA approach, another way to look at this problem is to look at the material and energy flow through the system. And as well as being a valuable exercise in its own right, it's also an important part of the development of through process models and some of the models that Michael has been talking about. And again, there's many approaches that we could apply here. Many of the most successful ones have focused on looking at material or energy efficiency, and they've combined that into a resource efficiency, which is effectively the useful output divided by the resource input, and also included the concept of exergy, the total available energy of a particular system. Next slide, please. And so this approach allows us to define the various process, the various resource flows, if you like. So we've got two examples here from Sun and from Gonzalez Hernandez. And again, it's a useful exercise in itself, especially when you can populate these diagrams, you can add figures to these diagrams, and you have a very sophisticated and detailed picture of your particular resource and flow, whether it be energy, whether it be materials, whether it be carbon. Next slide, please. It also allows you to drill down and examine parts of the process route in more detail. So here again is work by Gonzalez Hernandez from, I think, 2018, looking at the Boss plant at Port Talbot. And on the left-hand side, we have the wire diagram, as they're called, which shows the process structure and shows the system boundaries. And on the right-hand side, we have a Sankey diagram. And this is a Sankey diagram for a particular given day, measured in terms of exergy. So you can look at the inputs, you can look at the outputs. And of course, that lovely visualization aspect of a Sankey diagram allows you to quickly gain a detailed picture of how a system is operating. Next slide, please. And you can further drill down and allow visualization and of resource efficiency to be made. And so on the right hand side here, we've got 4 key steps in the process. We've got desulfurization, we've got the converter itself, we've got the tapping, and we've got secondary metallurgy. And we can look at how the resource efficiency of those 4 steps varies over time, in this case, over a period of 28 days. And on the left-hand side shows the resource efficiency over a number of batches. And you can see that sort of bimodal distribution, if you like. And this allows the reason for changes in resource efficiency to be hypothesized and identified, which in many ways I think is the most important aspect of this type of approach. You can identify your resource efficiency. You can also identify why you're getting variations, increases and decreases in that particular aspect. Next slide, please. And finally, we can use it to, another way to use this approach is to allow various scenarios to be compared. So here's some really nice work from Song et al. From a couple of years ago, which looked at 3 different scenarios. They looked at the integrated steel plant, the top gas recycle blast furnace, and the Corex alternative smelting reduction process. And again, those sort of pseudo Sankey diagrams on the right-hand side with the integrated steel plant at the top and the inclusion of the top gas recycle blast furnace at the bottom, again, allows comparison of these 2 approaches. And we know that the benefits of the top gas recycle blast furnace in terms of reduction of CO2 emissions. We also know some of the disadvantages of that approach as well in terms of variation in material quality. But having this visualization approach is really useful in quantifying new approaches and allowing for more informed decisions. And on the left-hand side, just to finish off, it's a graph that shows the CO2 emission intensity in terms of direct and indirect emissions for these 3 particular scenarios. Next slide, please. So I think there are many approaches we could take. All of them have their own advantages and disadvantages. All of them, if done properly with robust data, can be really useful. And there's a lot of approaches going on in the UK, a lot of similar approaches in the UK. Stephen Spoon is doing some lovely work down at the University of Swansea, for example. In task 5, intelligent steelmaking, we're going to be looking at the intelligent use of data to try and inform and improve steelmaking efficiency. And that's data for some of the real-time through process models that Michael has talked about, and the data that we're going to be using at Sheffield to identify efficiency improvements in terms of energy and in terms of materials. Next slide, please. So here are some of the aims of this intelligent steelmaking task. We've talked about the process models and the inventory of existing processes and resource flows, some of the various methodologies that we might use, and also trying to quantify what the impact of that might be. So to optimize for energy efficiency, for example, to reveal a transparent picture of the internal resource flows, material and energy of various steps in the production process. Next slide, please. Back to you, Michael. Okay, so at the very end, we want to give a
quick progress update on what is happening. So you probably remember the image from the digital refinery and these adaptive process models. So what we are following is a so-called effective equilibrium reaction zone approach, which is very handy in a way that you can use the size of that zone, of that reaction zone, as an additional variable in your simulations. And this way you are basically trading accuracy versus computation time. And you can either have very small zones and you have a longer simulation time, which will be more closer to actually finite element simulations. That is if you need accurate data, or you can actually have very quick data that might be a little bit less reliable, but can still be verified offline. One of these examples is actually the blast furnace stove that is on the image on the very right-hand side. You see in a nice color code, actually these individual zones. The Arash is actually modeling the heat and mass exchange, the corrosion that is happening. And you can change the size of the zones depending on whether you want to have more accuracy or you want to have fast predictability in these models. So that's a very important tuning parameter to make these approaches fit for whatever application you want. And I have to stress that this is just one case study, and there are many potential more. So we are always happy to actually discuss with whoever is interested to work with us to develop and apply this technique on other case studies as well. Because essentially this is meant to become a template for processes that are across the whole production route. So over to you, Richard.
So just a quick update with the work that we've done so far in Sheffield. It's been in collaboration with Liberty so far. We've identified initial areas of interest. We've received some superb energy and raw material data from Liberty, ranging over a period of time, and identified a number of work packages, including a comparison of the electric arc furnace performance, a comparison of ladle furnace performance, and we've already carried out some product life cycle inventories and assessments for 4 different steel grades. Next slide, please, Michael. So I think just to summarize, collection, interpretation, and analysis forms an integral part of any future smart, intelligent steelmaking strategies. And I'd like to thank the inputs from the UK steel industry so far. Been very valuable, and those conversations have been extremely useful. And just to finish off with a look at the team, myself, Michael, Arash, and Uchenna. Next slide, please, Michael. This was going to be another plug for the Materials Made Smarter Research Centre, but Ian mentioned that at the top of the session today, so I won't go into it. But in terms of circularity, it's a really nice way to finish off, because I'm going to hand over to the director of the Materials Made Smarter Research Centre, who's also the chair of this session. So back to you.